Ferguson, associate professor in our department. Scott got all his degrees from Buffalo. He got his BS both in mechanical and aerospace, and then his MS and PhD in mechanical. He worked with the current dean of University of Buffalo at the time. He's got a lot of awards. He's got an award, the National Career Award, NSF Career Award, and he got the Outstanding Teaching Award, the Young Investigator Award from ASME, and also the Mechanical Engineering Educator Award from ASCE. Scott works on a very interesting confluence of looking at product design, coming up with design methodology, and also looking at design optimization and bringing all that into traditional design practices, which some of his design practices are very focused on what happens in future events and stuff like that. So he's going to share a lot of that today and hopefully expand our viewpoint on how design and design methodology works in the modern environment. So Scott, take it away.
Awesome. Thanks, Srinath. That's a great introduction. So I'm thinking about how I wanted to kind of frame this talk. I titled it Pulling Back the Curtain. And really the idea here is that we have a lot of challenges that we have to face when designing consumer products and designing complex systems. And two of the big challenges that we have to overcome are how do we manage product variety and how do we navigate uncertain futures? And I'm going to hit on both of those themes today. And I want to kind of kick things off by having you think about these following scenarios. I want you to ask yourself, what's going on here? So, in these two photos, think about the environment. You're a consumer trying to make a choice. What are the things that you notice? What are the challenges that might arise, right? So we have shoes. This is just a picture from Dick's Sporting Goods. And then we have a car dealership lot. And the problem is that as a consumer who has to go shopping in this space, we have a plethora of choices. And each company or each manufacturer has to figure out how much product variety they want to offer and manage that against the variety that their competitors offer. Now, the idea of offering variety is driven by the idea that everybody is different and that heterogeneity offers up market opportunity. The challenge behind that, though, is psychological research has shown that if we offer too much variety, people actually suffer from what's called product claustrophobia. There's so many options that they honestly don't know what to pick. And when they do make a choice, they often find themselves very unsatisfied with it. And anybody who's ever been grocery shopping where you're just staring at an aisle of groceries of cereal can kind of get that idea. We start to lose the ability to really distinguish between concepts. So while variety is good, too much variety is bad. So where is that knee in the curve? And then the other thing that we're really interested is looking at the design of complex systems. So unlike consumer products, which come out maybe every year or every 18 months or every 2 years, people consume them, use them, and then replace them. Complex systems are really different. The design time behind them is incredibly long. The systems are incredibly expensive. And the problem is we have no idea what the future of these systems is going to be. There's going to be changing requirements, changing technologies, and changing operating environments. And we have to try to forecast what these systems are going to do. And it turns out that's really, really hard. We don't know a great way of doing it. There's two really great examples here. So the B-52 bomber, designed in the 1950s and 60s. The last one that was actually manufactured was in the late 1960s. They're still in use today, and they're expecting B-52s to be in use through 2050. So we're talking almost 100 years of lifespan of these systems being in service. And they've had to undergo many modifications along the way as new technologies and new missions come out. So what makes that system really successful? How do we keep it alive for 80 years? Now the F-18 is kind of the opposite story. It was a constant struggle in the requirements generation phase. And then after it came out, within 5 years, they had to redesign it so much that there was only 10% commonality between the first version of the system and then the redesigned aircraft. So, we started asking ourselves, what is it about the choice of system architecture that we make as engineers that allows some systems to be really successful in operating for the uncertain future, and some systems that really struggle with changing requirements in uncertain futures? And what do we do? How do we provide guidance? And that's where we want to start pulling back the curtain, right? We want to start giving designers and engineers tools that will help them navigate the challenges associated with these kind of design problems so that we can make the most informed decision. And the reason why we're interested in this is that we want to improve decision quality throughout the design process. It's being increasingly realized that engineering design is effectively a decision-making process, and it's a combination of economic theory, operations research, decision sciences, and other disciplines. And perhaps one of my favorite quotes is the idea that what we're trying to do by understanding the science behind engineering design is we're trying to help engineers make the best change in poorly understood situations with the resources that they have available. And how do we pull together the right information, help them process it in a meaningful way, and understand what the best change might actually be? It requires a lot of context, and it requires the combination of a lot of different theories from many different disciplines. And the work today that we're going to highlight shows how we've attempted to bring together a lot of these different theories to help engineers make better engineering design decisions. It would be horrible if I didn't recognize all the great people that I've had an opportunity to collaborate with since I've been here at NC State. On the market-driven product design side, we've done a lot of really cool work with Joe Dollinger, who's at Baylor University. He used to be at General Motors R&D. Mark Beltramo, who is still at General Motors Research and Development. And then also some of the work that I'm going to show you today has been validated and actually adopted by a company called Sawtooth Software. And I've had a really great experience working with Brian Orms and Walt Williams at Sawtooth, explaining to them what these techniques are, understanding the problems that they're trying to solve, and then helping them implement it in their software packages. The work on system evolvability and uncertain futures, we've had a really great opportunity working with Chris Mattson at Brigham Young University and Bishoy Marcos at the University of Georgia. And you'll see their name as we talk through kind of how we've developed that side of the evolvability work. And then I also have to recognize all of the current and former students in my lab. Not all of them can be represented in this talk. I had to make a lot of hard choices about what information made it in as I kind of build out my narrative. But it's been a combination of many, many students over the years who have really helped kind of guide this discussion and highlight some of the really cool things that I'm going to show you today. So there's two major research directions in my lab right now. The first is what we call market-driven product design. And this is really focused on the idea of understanding how we achieve product variety successfully, and then the optimization problems that get formulated around that. And just to kind of give you some grounding words that you're going to hear as I talk, we're going to talk about the idea of demand modeling or market research models. We're going to talk about how we've advanced optimization techniques in order to solve these problems. We'll talk about the idea of product platforming. And that's where we're going to implement commonality within our solutions so that we can attain economies of scale. One of the big challenges about product variety is when you have too much variability. Not only is it a burden on the consumer who has to kind of navigate through that space and figure it all out, but the other challenge is that from a manufacturing standpoint, the lack of variety or the lack of commonality and the more variety that we have means that we have more manufacturing kind of steps that need to be developed, more tooling, a bigger supply chain, more inventory, all of these challenges that drive up product costs. And then those costs eventually have to get passed on to the consumer. And then we're also going to highlight this idea of inverse design methods and how we want to rescope the problem in order to help us navigate this space. When we're talking about design for uncertain futures, the thing that we're going to highlight there is how do we achieve system longevity, and how do we view this in the perspective of the idea that these systems are going to be redesigned. We're going to talk about the challenges of requirements management. We're going to introduce the idea of change propagation, which is where when you have one change that causes other changes that come up down the line because of that. We're going to introduce our idea of component excess, and then we'll also talk about value analysis and why it's complicated and some of the interesting studies that we've been able to formulate to kind of tackle that problem. So I'm going to start with the idea of market-driven design. And some of the interesting ideas that we look at here are really kind of tied into a framework for decision-based design that was introduced by George Hazelrig. And George is a great character. I love George. He recently retired from the National Science Foundation, but he established what he perceived as a framework for how we can pose engineering design problems, right? And the general idea behind it is that we start with a system configuration, right? So we have a concept. We then understand what we can manipulate out of that concept. Those are our design variables. From those design variables, we get these system attributes, right? And those system attributes happen on many, many different levels. If I'm designing an aircraft, my system design parameters might be things like the coordinates of the airfoil shape, the length of the wing, the width of the fuselage. The system attributes are going to be more things that I care about from a performance standpoint. Those are going to be things like my range, my endurance, maybe my maximum speeds. All of those things come together, and there's going to be demand for the product. And that demand is going to be a function of the system attributes, the price, and then he acknowledges the idea that those attributes are going to, the demand for those attributes are going to change as a function of time. We then have to make decisions as engineers about what the right configuration is, and this sets up an optimization framework. And the 4 questions that we're particularly interested in is understanding how do our engineering decisions impact demand? What's the relationship between the choices that I make in terms of the variables that I control? And how does that then influence the thing that the person purchasing the system might actually care about? You know, if we're going to model demand, then we have to ask ourselves, okay, well, what models should be used there, right? How do I represent a market? You know, do I need to represent heterogeneity? What kind of things do I care about? What are the right tools? And do they then link with my system design variables? It turns out these problems become really hard to optimize. So then the question is, okay, if we're going to do optimization, how do we improve the algorithms that we use so that we have greater certainty in the type of solutions that we're getting out of it? Because really what we're trying to do is understand that trade space. We're trying to understand the value of the different alternatives so we can make informed decisions. And then, you know, if we actually have to choose a system design, how do I achieve the right product mix? You know, what is the right amount of variety that I actually want to go after? And we're going to hit on all of these different questions today. And to kind of help you scope it, this kind of hierarchical flow chart is going to link together how we think about things from an engineering design perspective. You know, we start out with this idea of design variables. And the way that it works is, as engineers, there are things that we control. And when we make a choice, we then conduct engineering analysis, and then we get some insight into system attributes. And that is the really great research that's going on in this department, right? Everybody is helping us get better understanding of how we understand the link between, if I make these configuration decisions, how do I, you know, better assess and get better models that tell me how the system might actually perform or behave. But there's another layer here. From these system attributes, I also then need to add a level of behavioral economics on top of it, and that's going to link my system attributes to my business objectives. And the thing that we're interested in is creating a bridge that goes all the way from the design variable space, all the way out to understanding how the changes we make there then influence the business objectives. Because really, you know, from a company standpoint, we want to understand the relationship at that level. And what we're doing is building the bridges between these different spaces and understanding then the ramifications of our decisions. So what is behavioral economics and how do we use it? Behavioral economics helps us approximate the decision process that's happening inside your head. So I showed you an example of a sporting goods store where you're looking at running sneakers and you're trying to make a choice of which one do you want to go with. So, you're standing there, you're looking at a series of options, and within your head, the idea is that you're trying to assign a utility to each of these different shoes. And you're saying, okay, well, if I think about it, there's cushioning, there's responsiveness, there's the type of activity that it's designed for, there's color, there's brand, there's price, right? You're putting together all of these different things in your head, and you're saying, which one do I want to choose? And the idea behind it, or the assumption that's being made in behavioral economics, is that you select the product that maximizes your overall utility. So you're going to assign a score to each of these, and you're going to choose the one that has the greatest score. Now, the problem with that is that utility view is inside your head. And as a scientist, I don't know what's going on inside your head, right? We don't have really great mappings of the human brain yet. But what we can do is we can build models. And what we're going to do is we're going to say, okay, that utility function, that value of u, is known only by you. But what I can do is I can create a model of your decision-making process. We'll call it V. And then there's going to be unobserved components, maybe features that you're considering that I don't include in my survey choices or when I'm asking you questions. And maybe also some of the error and correlation between these attributes that I'm not going to capture. So really what we're going to do is we're going to pose a model that's trying to represent that thought process that's going on in your head. So let's decompose that a little bit more. We're going to argue that that value within your head is a function of two different things. It's a function of product features or attributes, those A's, right? We're going back to that Hazelrig framework. These are the things that you might actually care about. So the responsiveness, the cushioning, the feel, the perception, the coloring. And then we're going to estimate coefficients in front of that model that then bring everything together. And then for each different product, we can go in and we can assign a score. And with those scores, we then can start to gain some understanding of how you might actually make choices. And that becomes a really, really powerful tool. Now, there's a lot of great work that has won people Nobel Prizes on how we go through and build these models of choice. And the choice of model form influences the amount of data needed, how easy it is to estimate these market research models, and whether or not heterogeneity is captured. And at its simplest form, one of the ideas is that you can look at the probability of a respondent choosing one product over another, right? And the way that we fit these models is we field a series of survey questions where you actually are asked to make choices. So we'll give you a couple options. Here's option A, B, and C. Which one would you prefer, or would you prefer none of them at all? And based off of each person answering a series of these choice task questions, we can then estimate these probabilities of choice. And if we look at this probability model and we make some assumptions about those unobserved terms, we can then come up with a probability of choice model using a multinomial logistic regression. In its simplest form, it doesn't capture heterogeneity. I show you this one because it's the easiest to kind of wrap your head around. But there's also a lot of really cool extensions that we've looked at in our work. Some of the ideas that we've looked at is how do we capture heterogeneity? And we've looked at the ramifications of different heterogeneous models and how they might guide our design decisions in different ways. There's also the idea of non-compensatory models. And in non-compensatory models, what they say is there's going to be some things that you're not willing to make trades on. There's going to maybe be some features that you would never consider, and that we have to then come up with more complex ways of modeling those decision rules. But I give you this equation because what it really does and why we're so interested in using these behavioral economics models is that it allows us to create a market simulator. And by having a market simulator, we can now really understand the impact of the design decisions that we make. So here's a little kind of toy example. On the x-axis, we have different respondents. So let's say there's 5 people in our who took our surveys and that we've estimated model coefficients for. And then the y-axis is going to be the probability of selection. And they have the choice between 3 different products. Product A is going to be our product, that's in blue. Product B is going to be a competitor's product, that's in orange. And then there's also the gray option, which is they don't really like any of them and they'd rather walk away from making a purchase at all and maybe come back to it later. And we can model now all of these different things. What we see here is that based off of the choices that we have made in product configuration, there's a really high probability of respondent 1 choosing our product. They like our product very much. What we also see is that respondents 2, 3, and 4 are not likely to choose our product, right? We are getting less than 5% share from any of them. Respondent 3 really likes our competitor. Respondent 2 basically hates everything that's on the market. This highlights opportunities for us, right? How can we offer another product or maybe change the configuration of the product that we're creating in order to better capture share from a larger number of respondents? We also see where there might be coin flips between us and the competitor. Here it's kind of 50-50. You know, what could we do to make changes to the product in order to drive that probability of selection more in our favor? And by capturing heterogeneity, we now have a greater ability to understand how the design decisions kind of propagate through this probability of selection to individual respondents. And then we can take that and build a larger perspective of how a global market might behave. Okay, so that's really cool, right? We now have a bridge. We can go from the design space all the way out to some business objectives where we can say, if I can model probability of purchase, I can get things like market penetration, I can maybe start to offer, or I can start to calculate things like profit, and that's really cool. As we build more complex models and as we look at transitioning to product lines, the design space becomes much more complicated. When we consider heterogeneous models, so we want to represent the variety that's within a consumer population, the design space no longer has a single optimum. It's got a lot of local minima. The space is incredibly bumpy, which means that analytical optimization techniques don't navigate these spaces effectively at all. And we need to look toward other algorithms that can navigate these bumpy spaces. The other issue is that the design space is often quite large. The reason that we even started looking at some of this work was we had been collaborating with people at General Motors. They were trying to solve some of these problems in terms of figuring out how to best design feature packages. And if you were only looking at making 5 variants of vehicles with the number of different features that they were considering and the different ways that you could combine them, there was 10 to the 43rd different options of design solutions. And it turns out that the algorithms that are available in traditional software packages were just choking on them and was not navigating that space very well at all. And that's how we got brought in. It started bringing us in as experts in optimization, can you help us navigate this space? And we've extended it quite a bit since then. The other thing is that these problems often tend to be mixed integer. And the ramification of that is that gradient information is often not available, right? There's nothing in between an engine choice of a 4-cylinder and a 6-cylinder. There, you know, being at 1.5 doesn't mean anything to me. So I can't really estimate the gradient. So what we really need to do is enhance existing heuristic optimization algorithms so that we can navigate this space more effectively. And where we started and had some of our greatest success was looking at this idea of how you put together the initial population. We gravitated toward genetic algorithms for these type of problems because we were interested in both single and multi-objective cases, and that, you know, they don't rely on gradient information. They're really robust at navigating multimodal spaces, but what we noticed was that the initial solutions were really bad. And the reason why is that the traditional way of making an initial population using a GA is that you just randomly sample the space. Now, for mathematical problems, which everyone loves to test, their optimization algorithms on, it makes a lot of sense. But for design problems where there's structure and correlation between some of these attributes, what you start to see is that you can get some really goofy things. It's possible that I can randomly pick a body style, an engine, and a wheel type and get something that makes a lot of sense, right? That looks like something that would go on a truck. I could also take the body style of a sports car, put a V8 engine in it, and give it some off-road tires, and now I get some solutions that really just, while they're possible, probably aren't going to be preferred by the market. And since those market objectives are the things that I'm trying to maximize, that's going to create problems. And we saw this in creating these initial populations. If we looked at our initial population scores, for some of the objectives, let's say we were trying to maximize share of preference, which is how many, the percentage of people that would buy your products. We were starting out in some of our problems at 17 or 40%, where the best final answer was 88% or 75%. So we're not even in the ballpark, right? We're not relying on the optimization algorithm just to tweak it. We're really saying you got to go a far way in order to make this solution better. And it turns out those spaces are really hard to navigate, and they weren't doing a very good job of that. So if the idea is that you would normally just randomly sample your space, what we did instead was we said, okay, well, let's strategically sample that space, but let's take a look at how people prefer product configurations and the features that they prefer. So we started looking through the different attributes and said, the more a feature is preferred, the more we should sample from it. And we should try to put together initial guesses that represent what people actually care about, and that'll give us better solutions. And it turns out that it worked really, really well. So we have two different problems that we've been using. On the left, we have an example of designing an MP3 player. On the right, we have a vehicle packaging problem. And that was the problem with the really, really big, complicated design space. In each of these two figures, the one on the left, those are the random initial populations, right? If you just randomly sample kind of evenly that design space and put together product line configurations, we see that those initial solutions are relatively low. We tried multiple different ways of strategically sampling the space using preference estimates as a guide. And what we found was that we could really improve the initial starting point for these algorithms. And then what became even more cool was when we started then letting it run, right? So for this example, what we see, or in this slide, what we see is that by targeting these initial populations using what people prefer, we either achieve a solution much more computationally efficiently, or we actually achieved a better solution quality that wasn't able to be achieved by the random initialization approach. So on the left, for the smaller design space, we find the same best answer, but we do it a whole lot quicker. On the right, for the more complicated and difficult design space, we find not only a better solution and quicker, but we find a solution that the normal approaches could never find. And that became really, really important, because how do we make good decisions and inform that design process if we're not even getting the right answers out of the algorithm that we're looking for? Okay, so that was how we started, right? We really had tackled this problem by saying we're optimization experts. How do we improve algorithm performance? But then we started thinking even more about the problem. We started saying, well, are these solutions any good? And a common phrase that I'm going to come back to is this notion of what's going on here, right? So, okay, but we're getting better solutions, but do the solutions make sense? Can I actually use them? And in this figure, we started pulling out some of the solutions and saying, okay, if we turn these on, do we see solutions that you would want to go with, or do we need to do some kind of repair? And we see some interesting things. We see one product, and I highlighted it in orange, where it has It's the only product of these 10 that have a single input type. Do I really want to offer one product that maybe only gets 5% a share? That seems like it's going to increase the amount of design effort, tooling effort, and manufacturing effort. Maybe I don't want to do that. Do I really want 5 different display sizes? That seems like a lot. And then, do I want a larger storage option if there's only one product that uses it? So it really makes us think, are these solutions having structured commonality? Do they even make sense in terms of what features are getting packaged together? So some of the things that we've started thinking about and been implementing is, okay, what we want to do is we need to establish pricing constraints. We want to make sure that low-end products are priced like low-end products, and that higher-end versions of the product are priced like higher-end versions of the product. We also want to make sure that we constrain the attributes so that there's some degree of content laddering, right? What we don't want to do is confuse the consumer in the product lines that we come up with. If product A has something like auto off, we want B and C to have that as well, right? We don't want really nice features on our low-end product that don't show up on the high end. At the same side, we necessarily don't want some of our distinguishing high-end features on low-end products, because then it makes it really hard for people to understand why they're paying more money for something on this product when it also exists on the cheaper product, right? So we want to establish these kind of controls between the different market segments that we want to capture. We also have been doing a lot of work looking at how we want to model component sharing. The idea of product platforming is the notion that you want to maintain common elements amongst all the product in your line. And there's a lot of great work by people like Tim Simpson at Penn State who have showed the benefits of product platforming. But if you rely on product platforming too much, you can actually do yourself a disservice. There's been some really great work that shows that sharing between low-end and high-end products results in either over-designed low-end products and higher unit variable costs. And with markets where you have extreme diversity in preference, platforms may not be appropriate. People have a hard time distinguishing what's going on between the features, or you're not actually able to offer people the different amounts of performance at relevant price points. So what we've been looking at recently is, how do you kind of tier commonality? What if I give you slight gains for achieving commonality within aspects of your within your product line, but not enforcing strict commonality throughout the entire thing? And we see advantages of doing this. So on the left, what we have are the examples of market penetration on the x-axis, a profit surrogate on the y-axis. And the colors in this graph represent the amount of commonality. What we see is that the products that have the greatest amount of commonality tend to perform the worst in terms of market penetration and the amount of money that we make. If we look over on the right, what we see is it's the same data points, but now I'm going to put a different filter on it, right? We're going to help engineers ask the question, well, what's going on in this commonality? What we see is that the green stars have 2 common attributes fully across the entire line. The red diamonds only have 1 common attribute. Blue solutions have no strict commonality amongst all of the products, but there's some inherent commonality amongst the subset of products. So the question then becomes, how do we build that in and what do we do with it? And that's what we've been looking at. Another challenge of these problems is, how do we navigate uncertainty sources, right? Uncertainty is really key. So there's parameter and structural uncertainty associated with defining my models. So, those behavioral economics models introduce uncertainty, and I need to worry about those things. There might also be uncertainty about my product attributes. Are they actually going to achieve the performance that I think the system is going to achieve if I configure it this way? Also, there might be uncertainty about component costs. And then there's also going to be uncertainty about what my competitor is going to offer. And we've been starting to look at these uncertainty sources. And what we have here, The black circles represent what happens when you only use the mean of a Monte Carlo simulation. The different ellipses represent the 95th percentile confidence interval when you consider some of the parameter and structural uncertainty in your models. And that's really important, because what we start to see is that there's variability then in what our model predicts of how each consumer is going to behave. And this is something then that we want to build into our procedures when we start navigating these design spaces, right? Are people buying our products, or are they actually switching to competitor ones? You know, are they moving between similar products, and do we see trends? These are questions that we're trying to answer and then bake into our optimization algorithms so that we can get more robust answers. While there's existing literature that talks about the idea of maximizing kind of a robust version of revenue or worst case revenue, we argue that that really looks at things from a product line perspective. Instead, we argue that we also want to consider uncertainty from a product share perspective, right? Is somebody flipping between our products? Are they flipping from one of our products to a competitor or the outside good? So in this example, right, our estimate of share is consistent because within each draw, that person is still choosing our product line, but how those individual products are going to be bought is going to be different. And that can impact the manufacturing and inventory decisions that we make. And that's going to be really important when we start talking about manufacturing and production. And what this allows us to do is enhance the trade space optimization approach, where we can start to look at the trade-offs that go between business objectives, manufacturing objectives, and customer response, and use then multi-attribute decision-making tools to help them make final selections, right? To help the engineers get a better understanding of what's going on in their problem. Some of the more recent work that we've done has also started to look at how we want to model the problem and the different things that we want to consider. We've been putting it in the context of the marketing mix. And this is a really cool paper that we just got published in the Journal of Mechanical Design, where we talk about how the different considerations of how we market the product, the retail channel that we put it in, how we maybe want to promote the product to the consumer, how we want to price it, puts constraints on our design problem formulation that is going to impact the design process itself and take away some alternatives. An example for promotion might be if I'm designing a pickup truck and I'm going to say as a marketing tool that we have best-in-class towing, that's going to flow all the way back to the engineering design decisions that we make, because we have to make sure that when we model the system and do our analysis, its tow capacity is going to be best in class. So that encourages more communication between the different layers within a company, and it also then impacts the choices that we make as engineers. I showed you this relationship where we went from design space to business space, but really the cool problem is what happens when we flip this on its head. Really what I want to do as an engineer is I want to say, if I have a target in the business objective, then that's going to map back to a series of solutions in my system attribute space. And that's going to map back to the different feasible regions in my design space that are going to allow me to find and achieve those business objectives. And if we can design tools that help this inverse mapping problem become more efficient, we can take engineer time and allow them to really understand the trade-offs that they have to make, rather than kind of hunting and pecking around these giant design spaces, hoping that they find a solution that achieves the goal they want to achieve, right? And that's going to allow them to kind of pull back the curtain and really understand, okay, if I care about this objective, what are the choices I have to make? And then we can start to explain those to the engineer themselves. So that's where we think this work will have its greatest impact. Okay, so that's product variety and optimization. Now let's talk about uncertain futures. And the difference between them is that we're going to argue that in product variety for consumer products, we generally can think of it as a small world problem. We understand the consumer at a given moment in time, and the estimates that we make are going to be okay. But future prediction, that's really hard, right? And we're interested in this idea of system evolution because I would argue predicting the future is impossible, right? We have to look into the crystal ball of operating requirements, operating environments, new technologies. We can't even predict what the weather is going to be in a few days. You know, how are we supposed to predict what a system is supposed to do in 5 or 10 years or 50 years in the case of B-52 Albert? And there's this really great book. I love it very much. It's called Radical Uncertainty by John Kay and Mervyn King. And I highlighted a couple elements from this subset of text that I want to share. It's the idea that we want to avoid the pretense of knowledge, right? Bogus quantifications where we have to make up things that we do not know and could not know. And what we really want to do instead is ensure that our plans are robust and resilient to a range of plausible alternatives. And that's going to become our clarion call for evolvability. I don't want to assume I know the future. I'm gonna throw my hands up and acknowledge I don't know what the future holds. But what I'm going to do is understand how my system architecture decisions impact my ability to respond to different future scenarios. And if we can design systems that are more capable of being responsive to these changes through redesign, then we can achieve effective systems for uncertain futures. Okay, so there's this notion of margins. And Claudia Eckert recently put out a really great paper where she was looking at this idea of defining the difference between buffer and excess and margins. And we're going to tie into this. So we've been working in the excess space. We started with Chris Mattson back in like 2014. And the idea behind it is that, you know, buffer is helping us design for the known unknowns, right? The things that we can put probability distributions on. Excess helps us really get ready for the unknown unknowns. And there's an underlying hypothesis of excess-focused research that we can increase system value by reducing sensitivity to requirement changes, and then we can truncate change propagation. We looked at how system interactions and change propagation are modeled in the literature. The first thing that we looked at was this idea of representing systems using design structure matrices, right? Understanding how there's interactions between components within a system. We also looked at the idea that it's really the interfaces between components that might be the handcuff. And those type of things rely us to look at functional modeling, where we break systems down into their functions and look at the flows between those functions. And then we also have this idea of change propagation. How do we look at the impact of and likelihood of, if I make a change in one component, is there a likelihood of it impacting other components? And then running through probabilistic calculations that say, okay, if I make a change in A and it's going to cause a change in B, what's the likelihood that that then causes changes in C and D? And then from that, we can get these combined likelihood scores. And what we've been doing over the last few years with Chris Mattson and Mishore Marcos and the students in my group, we've been understanding how to bring together these different technologies to help us gain better insight into the ramifications of our original system architecture and how it's going to allow us to either accommodate redesigns or handcuff us and prevent us from achieving redesigns. So we started out by just taking some really simple systems, quantifying key interfaces, and then identifying architecture bottlenecks. So we started out with something as simple as a Nerf gun in one of our examples. And it turns out people are willing to do some really crazy things to Nerf guns. They're putting electronics in it so they can have laser pointers, or they can change the firing mechanisms, or they can automate the system and turn it into a little turret. So we started looking at this idea and saying, okay, if I can identify the major components, the major interfaces between those components, and then quantify those interfaces, I can use that I can then go through some different scenarios of alternative futures, and I can identify which components are affected the most by some of the proposed changes, and then which ones maybe prevent me from actually achieving some of those changes. So we can say, okay, if I go through a series of changes, in this case, for the futures that we envisioned, the rotary barrel was changed the most often in order to accommodate some of these new ideas. We really want to pay attention there and make sure that we design it in such a way that it can be adaptable and redesigned, and that it works with the air directing seal more effectively. We've also then simulated what happens when excess is consumed. So this idea of going through direct likelihoods and saying, does one component, the likelihood of it changing another component, going through a series of probabilistic calculations and getting those combined likelihood scores, we could then go through for a given system and we could get a better understanding of something that we call the average number of changes per change, right? So how many components, as we start kind of going through and redesigning a system, how many components are affected by the changes that we want to make? And then we said, well, we can simulate this. And we actually incorporated excess into our analysis under the idea that it would reduce the likelihood score. And then with each change, the likelihood would increase because that excess was being consumed. And what we started to see was that initially the system changes per change were low. And then as we started to make more redesigns of the system and we modified the system in more ways, more and more components had to be changed because their excess was consumed. And that was really cool. We looked at network theory and hubbing, and we came up with some general principles about how components are connected and how it impacts this changes per change calculation. But really what we wanted to do is we wanted to find some quantifiable evidence about the value of excess. And there's a lot of really nice qualitative evidence and anecdotal stories, right? We've talked a lot about the Boeing B-52. The Tesla Model S, cool story there. It's been put into the field with more sensors than they're actually using. And the reason why, they want to bring some of those sensors online when their software capabilities catch up to it. But what they know is that it's going to be a lot harder to bring a car back in and install additional sensors as needed than it is just to flash your software update and go through and do that. MakerBot has also been looking at the idea of how you can design the system to be evolvable over time, and that's really cool. But quantitative studies are really, really hard. We need information about how requirements change after a system's been fielded. We need information about component pricing so we can model those upfront costs and the costs associated with redesign. And we need to understand how system performance and component interactions are impacted by requirement changes. And getting this information is really complicated, but we came up with a really, really cool and slick example. We designed a study around desktop computers and video games. The reason that we did this is we have data about how requirement changes happen by looking at video games. Video games give us information about minimum system requirements and recommended system requirements. Minimum system requirements tell you what your system needs to have in terms of its components in order just to play the game. Recommended requirements are what you need to have in the system to play the game at an enjoyable level or at the highest level, what the game developer recommends, right? That means the best visuals, the least amount of lag, the quickest load times. And my student Daniel scraped data for over 5,000 different game titles from 1996 through 2020. And what we found by looking at scraping hardware data and video game data is that purchasing lower end components really limits how well future requirements can be met. What we found is literature suggesting that people tend to upgrade their desktop computer every 5 to 7 years. I'm in need of an upgrade. My computer is about 8 years old. When we look at the CPU, what we see is that CPUs in the first quartile do not play games more than 6 years out after 2006, right? So by then, you're falling below the median game requirements. Now, those fourth quartile CPUs, those games are capable of playing games 8 years to sometimes even 10 years after their release. Now, CPU is interesting. Even more kind of effective at telling our story is the idea of the GPU, or the graphics card, right? What we see here is, again, looking at that 6-year component life, we see that GPU cards below the 75th percentile maybe only last 4 to 5 years, where the lowest end GPUs effectively can't even play the median game at all after they've been released. You know, so that's really kind of eye-opening. You know, how do we strategically make these decisions? So that led us to going through a study where PC Gamer, a computer gaming magazine, and part of the reason we had this idea is when I was growing up, my mom actually worked for a company called Electronics Boutique, and they sold video games. And she would bring home the magazines because she was supposed to learn about the different games. And then, you know, being a middle and high school student, I would read through those games as well. And every year, about twice a year, they would post these issues where they would recommend dream, mid-range, and entry-level computers. And it was supposed to help somebody who didn't know what they were buying, how to get the best bang for their buck at 3 different price points. The cool thing about it is we now have information about all computer components, their prices for these 93 different configurations. And we also then have ways to relate those to technical specifications, so GFLOPS for CPU, texture fill rates for GPU, and compare that against video game requirements. What we also did then was model or come up with a metric of how well these different systems could play the games that came out after they were introduced. So we look at a system life of 6 years. R of I represents the importance of each game, so we can score that. And then we also started to ask ourselves, how well does the system play the game? It was U of I of 1 if it met recommended requirements. We could scale it between a score of 0 to 1 if it just met minimum requirements. And then if it didn't meet those minimum requirements at all, we would give it a score of 0. We also then considered the total number of games that were released within a given year. And from this, we could calculate a system performance score that gives us an idea of, once a system is bought in a given year, if you look 6 years out of all the games that are being released, how good is that system at playing games? So here we have results for the Dream, Mid, and Entry-level system. And what we found is that it supports our hypothesis that more access in a system, right, those higher end components, allow more games to be played. And we can see this by putting a line at 1/2, because 1/2 on this SPM score means that you're beating the minimum requirements on average. You have systems that can play recommended requirement games or games at their recommended requirements, and we see that only with Dream and Mid systems. The entry systems that don't have enough excess can't play those games. So excess allocation also must be strategic. We then started looking at the balance between the ability to play games and the cost of the system. And what we see here is that over time, depending on how you weight the ability to play games and the cost of the systems, we start to see that, you know, the mid and entry level system actually have some value. But really what we were interested in is, can systems then be redesigned, and what become the bottlenecks of my architecture? What we looked at over time was that initially, you know, what components stopped me from being able to play games over those 6 years? Initially, RAM was the initial bottleneck. Then the GPU became that initial bottleneck. What we also found then was that within a system, you could upgrade individual components so that you could play more games and give that system more increased value. And doing something like increasing the RAM of an entry-level system gave you a 14% playability improvement and only something like 7% of system cost. So we really started to get some insights and now have some quantitative evidence that we need to embrace the idea of strategic inefficiencies. And we've started to see this even with COVID, that, you know, having optimal efficiency maybe isn't exactly what we want, right? How do we accommodate uncertain futures? Our argument isn't to over-design everything, but to be strategic about it. And that's the idea of embracing strategic inefficiency. We have to really understand the implications on system architecture and then look at how we appraise excess. So what I want to do in the last 2 minutes is kind of talk about where I see a lot of our work going. COVID has really changed the way that we've thought about doing some design efforts. We have some really interesting questions that we want to ask about. For the first time, we see a citizen army creating products, right? Very rarely do we have multiple different design teams doing exactly the same thing. So we want to start digging into what factors cause these teams to form, how do they communicate, how do they understand the requirements associated with the products, especially considering many of them maybe aren't experts. Then we also want to look at whether or not these designs should be standardized so that we can leverage existing manufacturing aspects, especially when there's disruptions in the supply chain. In terms of system evolvability, what we want to look at is going back to this idea of radical uncertainty. There's this notion of narrative. And really that what we want to understand is the personal experience and the experience of others. And if we don't know what's going to happen, we want to see if engineers who are designing systems are actually retaining as many options as possible. So one example could be, you know, personal private business aircraft are often designed and then redesigned when somebody new buys the aircraft. So they'll make some modifications to the interior cabin. We could go out and interview people who are designing the interior cabin the first time and see how they're thinking about the future and how they're maybe designing the cabin so that it can be updatable. And then also go to companies who have to redesign the cabin and say, what do you wish people would have done to make your job easier? And see if there is alignment between how people are designing the systems originally and what they're trying to do on the back end when they're redesigning it. And then the last thing is when we're thinking about product variety, there's a really interesting question about product customization and interconnected systems, things like the power grid, you know, designed for the developing world. The assumption that you maximize your utility is up for debate. Right? It might be hierarchical. And there's this idea of a product hierarchy of needs, where we maybe look at things at a functionality perspective, then reliable, then usable, proficient, and creativity, and that you can't achieve those higher levels on the hierarchy without satisfying the things at the lower levels of the hierarchy of needs. So what does it mean to maximize? You know, can people not understand customization because it doesn't achieve some basic functionalities or reliabilities, and they can't even think about how to make the system more proficient or really express their creativity? So we want to kind of push on this idea of, you know, what do these models look like when we're really trying to get into individual behavior or understanding social impact? And then, you know, we've been working with people in the department. I introduced this idea of inverse mapping. Where we want to take this is using physics-based machine learning for inverse design. So we've been doing work with Mark Pankow, where we've been trying to understand how you can take results from FEA simulations and put them into a machine learning model so that we can get better predictions for inverse design by looking at data from, for example, material properties, so that we can turn our models into predictive design tools rather than just predictive analysis tools. I want to thank all of the funding sponsors who have funded our work. It's been a great time to work with federal agencies, individual companies, private industry. There's a lot of work that I didn't get to highlight, but I hope that this talk kind of just gives you a taste of what my perspective of engineering design research looks like. I hope you understand why I'm so passionate about it and why I believe it's so important, why it has rigor and why it has value, and why it's something that we really need to teach all of our engineers as we prepare them to enter, into the next phases of their career, so that we can help them understand the really big complexities associated with these design problems, because it's much more complicated than we often tend to think about. And with that, thank you all so much for paying attention today. And I'd love to take any questions that you might have.
All right, we're open to questions. Questions? I think people are still trying to wrap around all the interesting stuff that you mentioned, that I don't think many people have thought about choices that we make on a daily basis, that how that goes into design, not only for short term, but also long term too.
And that's really the whole point of this, is that, there's a lot of decisions that go into the design process, and we need tools that help them understand the ramifications of the choices that they're making.
Hey Scott, this is Matt. I've got a question for you.
Yeah.
First, really interesting stuff. One thing I've noticed, especially in things like consumer electronics, like cameras and phones and things like that, is sometimes the manufacturer will have different kind of release dates or release cycles for products throughout the year. And they might release kind of the low-end products at one point, and then high-end products kind of come later. And because of that, sometimes new features get incorporated into the low-end products first. And I'm thinking about what you talked about there, where you want to have kind of clear differentiation between those product lines. So do you think that's a mistake? That
No, that's a great question. And that's why we were actually interested in this design for the marketing mix idea. How you then promote, sometimes you might use a new technology in a low-end product just to see if people are really interested in it, or, to try to get just in the hands of consumers, so that then it creates better word of mouth, and then people are willing to buy it in the high-end products. So there's a lot of different things that go into those product line optimization decisions. It might be, we want to test a new feature, or we want to create some buzz about it, and that's going to override maybe what you would normally do. And capturing that interplay between what the marketing people want to do, what you can manufacture, new technology development, and developing that as a product line perspective becomes challenging, because then you also have to say, okay, I knew a technology is going to be coming out. Do I leave room in my system architecture so that I can accommodate this new technology next year when I do a refresh? Because I don't want to have to redesign the entire architecture because we actually got this new camera ready. And you see that with the iPhone, right? Where when they take it apart, when people do analysis, they'll see leftover space. And to some extent, that's that notion of excess of, we're going to leave extra space in this product, knowing that next year we're going to be introducing a new technology, so that we don't have to redesign the placement of all of our components.
Very interesting thoughts.
Any other questions? I think we're certainly over time, Scott. So let's see if we can give one more question, and then we can close the session, to close the activity. Hugo.
Yes, Scott, I'm just thinking about, this is actually very, very interesting area. Most of our faculty do not really get involved on this. But on the other hand, I was thinking that you talk about inverse design, or I believe that machine learning can really help this a lot. What do you think about, combining that with your field?
I totally agree. So, I think there's two facets to how I want to do research in this department. I think there's one facet is there's these challenges that I think from a design science perspective need to be addressed. And there's funding agencies and industrial partners who will fund that work. I think that we can also then bring our design tools that use optimization, trade-off analysis, machine learning, inverse design to help other faculty in the department navigate some of the challenges that they face in their problems. And you know, that's kind of the two elements of we have a lot of technology that's transferable to your type of problems, and I mean the global you in terms of the department. And I would love to find ways to collaborate with more faculty in our department. You know, I've done a lot of great work with Andre and Greg and Matt and Mark Pankow, and Landon and I have a few projects, but Brendan and I work together. I don't want to leave anybody out. But you know, how do we bring some of our design tools and you know help you solve some of the challenges in your problems is a very, very relevant and ideal question.
Wonderful.
I can vouch that Scott, me, and Ashok actually put together a very interesting machine learning based project design for some very high-end technology. But unfortunately, we got great reviews, but we didn't get funded. But it was a lot of effort that Scott put in to try to bring some of his design methodologies into more applied stuff. And that was where I think the future lies ahead for this kind of work is like, how do you collaborate with, I think Fugo said structural health monitoring has a lot of data that comes out, and then you could take that and put that into design and see how the next product could address some of the deficiencies in the previous product too. So.
And you know, if you look at this inverse design slide, don't worry about what the axes are labeled, but just think of it as a hierarchical design process. You know, if I'm designing an aircraft, the objectives on the left-hand side, that higher level, might be things like range and endurance. At the mid-level, it's going to be the wing design and the fuselage and the tail. And then the lower level on the bottom right are going to be things like the airfoil shape and the materials that I choose. So, you know, this inverse design idea that uses machine learning, it doesn't have to just navigate from design space to business objectives. It's really just any hierarchy. And you could be hierarchies within a complex system where now you have this linking of variables to capabilities to then performance measures in things like aircraft or vehicles or, you know, even material systems where you're going from a micro to macro level to, you know, some kind of desired performance.
So I'm going to give back people the time. So Scott, thank you, and I really enjoyed the presentation. It's very eye-opening to see design in a very different perspective. I think I knew about it, so I'm glad that other faculty also got to see, and our students also got to see what your group is doing, and also with all the other involvement in industries and research faculty, other schools. So thank you again, and hope everybody has a great weekend. I heard weather is going to be fantastic. Sorry for the weather today, but Saturday, Sunday is going to be great, and enjoy it. And thanks again, Scott. And
thank you guys. Thank you very much for the opportunity. It was a lot of fun.